Hi everyone, Dr. Burns here with our next lesson in our acid-base and solubility equilibria chapter. Here we're going to be discussing solubility equilibria. Now, up until this point, we've reviewed a few of the reactions that we've talked about generally in General Chemistry 1, the first of that being acid-base reactions. Now, solubility equilibria has to do with a different type of reaction that we touched on in General Chemistry 1, and that is precipitation reactions. Now remember, in a precipitation reaction, we had a solid that would go into solution. It would separate into its individual ions when put into solution if it was soluble in water. And we looked at solubility, on if certain compounds were soluble using a chart. Hopefully you remember that. But now we're going to dive into that, again, just like we did with our acid-base reactions, now with solubility and discussing how that's actually a form of equilibria as well. So solubility equilibria are established when the dissolution and precipitation processes occur at equal rates. So remember, equilibrium is when the rates are equal to forward and the reverse reaction. So in this case, our forward and reverse reaction is the solid going into solution and the solution coming out and going into a solid. So that's just our equilibrium there, and those are at equal rates. Now, the quantitative prediction about how much of a given ionic compound will dissolve in water is possible using a solubility product constant, which we denote as Ksp. So this, since it's an equilibrium, is just another equilibrium constant, but it's specific for solubility. So here we have the equilibrium of silver chloride in equilibrium with silver ions and chloride ions, and this is essentially what's going into solution here. So here's our silver chloride, and then we can see in our next image that we have some silver ions. Silver are going to be the gray ones. Silver ions and some chloride ions, but we also have some that's still a solid. Okay, and this is an equilibrium, so if one chloride ion goes back into the solid, another chloride ion will come out of the solid, and that's the equilibrium that's happening between the solid and the ions. Now the KSPs, these equilibrium constant expressions for our solubility product, is actually a lot easier to write than our equilibrium product or equilibrium constant expressions that we've worked with previously, because when we're working with these, our reactant is always a solid. And we know from our experience with equilibrium constants that solids don't get considered when we're talking about K values. So our KSP for this reaction is just KSP is equal to the concentration of the silver ions multiplied by the concentration of the chloride ions. So let's look further into this KSP value. The SP of KSP stands for solubility product, if you didn't see that already. And the KSP expression can be written just like all of our previous equilibrium constant expressions, except we have to remember that the solid does not contribute. So here I have a bunch of compounds that are dissolving in equilibrium and their KSP values. These KSP values can be found in the data tab on ALEKS, as well as Appendix 3 in your textbook. Okay, so you can find those values in two separate places. And again, there's more of them. This is just 5 of the many. So what I want to do here is write the KSP expressions for these solutions. So we have to remember that these Ks are still going to obey our rules of equilibrium expressions. So it's going to be the concentration of the products over the concentration of the reactants raised to their molar quantities from their balanced chemical equations. We have to remember that if they have a coefficient out in front, that we have to raise them to that coefficient. It's been a while since we've looked at that because we've been looking at weak acids, weak bases where everything's in a 1-to-1 ratio, so we haven't had to worry about that. But when we're looking at solubility, we do have to worry about the balanced chemical equation because these are ionic compounds, okay? So we have to balance them with coefficients to balance out the charge. So our KSP expression for our first one, the dissolution of aluminum hydroxide, is going to be KSP is equal to the concentration of Al3 plus times the concentration of OH minus. However, we have to raise it to the third because of the balancing with the 3 out in front of the OH. We're not multiplying it, we're not dividing it, we are raising it. So K is, remember, we raise it to that power. Our next one is calcium fluoride. So our KSP is going to be the concentration of the Ca2 plus and the F minus. And it has a 2 out in front of that fluorine, so we're going to square it. Okay, you try the last 3 on your own. These ones are a little bit simpler because everything's in a 1-to-1 ratio. So we have KSP is equal to the concentration of Ag plus times the concentration of Br minus. We have KSP is equal to the concentration of Ag plus times Cl minus. And our final one, KSP, is equal to the concentration of zinc 2 plus and the concentration of S2 minus. When you're writing these, make sure you account for the charge. Okay, we always want to put our charge in there so that we are making sure that we're first using the correct balanced equation. Remember, our ionic compounds can sometimes have different charges. Okay, we can have, zinc 1, zinc 2, copper 3, iron 2, iron 3. So we have to account for those appropriately and make sure that we're looking at the right dissolution equilibrium. And then when we're writing it, show our charges in there so that we make sure that we know that we're getting the right one, and also to show that it's of the ion, not of the elemental form. So if we know the KSP expression, and we know KSP is a constant, if we know one of the other concentrations in that expression, we can solve for the unknown concentration. It becomes a 3-value problem where 2 are known and 1 is unknown. So let's practice using those KSP expressions and solving for concentrations. So here we want to calculate the concentration of the ions in the following saturated solutions. So we want to find first the iodide concentration in a silver iodide solution, where the silver ion concentration is 4.3 times 10 to the minus 7 molar, and our KSP is 8.5 times 10 to the minus 17. So we have, we first want to write out our balanced equation because that's what's going to tell us our KSP expression, and if we have to raise it to any value. So we have AgI is going to be in equilibrium with Ag plus I minus, meaning our KSP expression is going to be equal to Ag plus and I minus. Since we know this is a dissolution, we know that the AgI as itself is a solid and that these are aqueous, so you can write that in your equation as well, your reaction. Okay, so now that we have our KSP expression, we can plug in our values. So we know KSP is 8.5 times 10 to the minus 17, and that's equal to our silver concentration, which is 4.3 times 10 to the minus 7, multiplied by our concentration of I minus. So let's grab our calculator so that we can solve for that concentration together. So we'll take 8.5 times 10 to the minus 17 divided by 4.3 times 10 to the minus 7. And we get that the iodine concentration is equal to 2.0 with sig figs. 1.97 rounds up to 2.0 times 10 to the minus 10 molar. And that is our concentration. Okay, now you try the next problem where we want to find the aluminum concentration in aluminum hydroxide solution, where the hydroxide ion concentration is 9.5 times 10 to the minus 8 molar, and the KSP is 1.8 times 10 to the minus 33. Remember to write out your balanced equation first and your KSP expression first so you can account for any balancing that needs to happen. Luckily, we had this KSP expression on our previous slide, so it's not too difficult. So we have aluminum hydroxide is going to be in equilibrium with an aluminum 3 plus 3 OH minuses. So our KSP is equal to the concentration of Al 3 plus times the concentration of OH minus that we are going to cube. So now that we know that, we can plug everything in. Our KSP is 1.8 times 10 to the minus 33. That's equal to the aluminum concentration, which we're finding, times that 9.5 times 10 to the minus 8, and we have to cube that value. So we'll do 9.5 times 10 to the minus 8, and we will raise that, let's put some parentheses in, raise that to the third. Okay, and then we'll do, let's see, 1.8 times 10 to the minus 33 divided by that value of our OH cubed. And that's going to give us our aluminum concentration, which is equal to, let's see, 2 sig figs here, 2.1 times 10 to the minus 12 molar. Now these types of calculations are pretty straightforward if we know the concentration of at least one of our products and our KSP. However, as we know that there are sometimes problems that we're given where we don't know those concentrations, especially at equilibrium. So we have some additional calculations that we can do that involve KSP. Before we do that, we want to just define two terms that we use to express solubility. The first one is called molar solubility, and this is the number of moles of our solute, which is whatever's dissolved, in 1 liter of a saturated solution. So if something is dissolved in solution, it has something dissolved in it, is a saturated solution. We know this is molar because it has units of moles per liter, which we know is molarity. So molar solubility has units of moles per liter, also known as molarity. The other type of solubility is just called solubility. So when I just say plain solubility, this is referring to the number of grams of that solute, whatever is dissolved, in 1 liter of a saturated solution. So solubility by itself is in units of grams per liter. We can convert between molar solubility and solubility using the molar mass of the compound. So if we're talking about molar solubility, we're talking about moles per liter as our units. If we're talking just about solubility, we're talking about grams per liter. And if we need to convert between those two values, we can use the molar mass of the compound that we're looking at. So when we're wanting to calculate a compound's molar solubility, so something in moles per liter, since this is an equilibrium, as we saw before, the first thing that we're going to want to do is construct an equilibrium table, so an ICE table. And then we're going to follow our rules of ICE tables where we fill in what is known and we determine our unknowns. For most of these, we're solving for that molar solubility, that X value. So we have to remember that the X that we get out, X in an ICE table, is in units of moles per liter, which is molar solubility. So if we're using an ICE table and we get an X value out, that's going to be molar solubility. If the problem asked for just the solubility, we would then have to use the molar mass to convert to solubility, to go from moles to grams. So just like we saw with acid-base reactions, the way that we're going to approach our ICE tables is going to be the exact same way we learned it in our previous chapter. However, just like with our acid-base equilibrium ICE tables, once we finish our ICE table, we're just going to have to go one step further in finding the final answer. With acids and bases, it was using the H+ concentration to find the pH. With solubility reactions and precipitation reactions, we're using that equilibrium concentration to convert from moles per liter to grams per liter, as long as the problem denotes that it wants solubility instead of molar solubility. So let's look at a problem that I've done already that kind of explains that. So we know that the KSP for silver bromide is 5.4 times 10 to the minus 13. We want to calculate the solubility. So automatically we know that we want our final answer to be in grams per liter. So when we want to set up our ICE table, we have our balanced chemical equation where we have silver bromide in equilibrium with silver ions and bromide ions. We set up our ICE table the same way. The best part about ICE tables with precipitation reactions is that the reactant side is completely ignored because it's a solid. So we don't even care about that. That's going to make solving these problems a heck of a lot easier, trust me. We won't even have to worry about approximations or quadratic equations or anything like that. It's going to make it a lot easier to solve, as we'll see. So we know the KSP of silver bromide. Before we even put the silver bromide into solution, the initial concentrations of our ions are 0. So that's before we've put the solid into the solution. We know the change in the concentration is going to be a plus X and a plus X. Here we have them denoted as S's to show that it's solubility, but you could show them you can show them the same as plus X and plus X if you wanted to keep it the same way. They just show them with S's in your book to show that this is a solubility ICE table instead of a regular ICE table or an acid-base ICE table. So they use S for solubility. So our equilibrium concentrations just become S and S or X and X. We can then plug that into our KSP expression. We know that the KSP is going to be equal to the concentration of the silver ions multiplied by the concentration of the bromide ions. And we know from our ICE table that those two values are both equal to S. So this gives us S times S is equal to 5.4 times 10 to the minus 3. So I'm going to fill in the blank from here to here. We get 5.4 times 10 to the minus 13 is equal to S squared. Or if you wanted to do like we saw before with our regular ICE tables, X squared. Whatever variable you use in your ICE table is fine. You want to use W, go for it. You want to use B, go for it. As long as you know that that stands for the change. That's all that matters. Okay. So we get 5.4 times 10 to the minus 13 is equal to X squared, which we can easily solve for with X. Okay, so we get 5.4 times 10 to the minus 13, and we do, let's see, the square root of that. So we get 7.3 times 10 to the minus 7, which is what we see here. So that is then the concentration, the molar solubility for both Ag plus and Br minus. That molar solubility, so we'll write that here, this is molar solubility, is also that of AgBr, silver bromide itself. So for the overall system of silver bromide. So that 7.3 times 10 to the minus 7 is the concentration of the silver bromide. So we know that that has units of moles per liter. And if we want to find the solubility in grams per liter, we're just going to use the molar mass of silver bromide to convert from moles per liter to grams per liter. So we'll multiply by the molar mass. Okay, remember molar mass has units of grams per mole, so the mole cancels on the top and the bottom, leaving you with grams per liter. So that gives us a solubility of 1.4 times 10 to the minus 4 grams per liter. So what did we just do? Well, we did our ice tables like we've done in the past. Everything was the same up until this point. Okay, and then everything down here is just our conversion from molar solubility to solubility. And we know how to convert from moles to grams. We've done that. We've been doing that all throughout General Chemistry 1 and 2. We know how to do that conversion. We're just using it here in a different respect. Let's practice another problem with this. So the KSP of lead fluoride is 9.8 times 10 to the minus 9. Calculate the solubility and the molar solubility for this compound. So we're going to set it up the same way. We want to start with our balanced chemical equation. PbF2 is in equilibrium with Pb2 plus 2F minus. Remember, we have to balance. We're going to set up our ice table. We could ignore our first column because that's a solid. And we know that our initial concentrations of our ions originally in solution are 0. Before I put that solid into solution, I don't have any ions. My change is now going to be plus x and plus 2x. Remember that if this has a coefficient out in front of it, that coefficient gets brought down into the change column, leaving my equilibrium column as x and 2x. So now that we have our ice table set up, we can plug everything into our KSP expression. So we know, I'm going to write it over here, that KSP is equal to the concentration of lead times the concentration of fluorine. But again, there's a 2 in front of that, so we have to square it. Now that we have our KSP expression, we can plug in our values. So we get KSP is equal to, what we know the KSP, we can plug in that value, I guess. We can just put numbers to it. KSP is 9.8 times 10 to the minus 9. And that's equal to x times 2x squared. So we have to remember that we take our balancing into account in 2 places. And that's where I always find students get stuck in these problems, is they either forget the square here, or they say, well, I'm already accounting for the 2 here, so this 2x that I have here is actually not existent. And they just put an x, and I don't know why, but they just get caught up in where the balancing is being accounted for. So just remember that you do account for it in two different places. That's how we started with these KSP or K-value expressions back when we introduced equilibrium. We accounted for the balancing in two separate places. It's been a while since we looked at balanced equations that have coefficients other than 1, so let's just bring it back to the front of our head, the front of our brains, that we account for balancing in two places, and we don't want to forget that. So we put the 2x in, and then we square that. So now we just have to solve for x. So we can simplify this. This becomes 9.8 times 10 to the minus 9 is equal to x times 4x squared. And that simplifies even further to 9.8 times 10 to the minus 9 is equal to 4x cubed. Okay, this right here, we have to remember algebra and simplifying. Okay, whenever you have a chemical equation where you have coefficients, you're going to have to do some algebra and simplifying there. So we have to remember how to do that. Okay, so x times 4x squared becomes 4x cubed. Okay, and now we can solve for x. So to solve for x, we have to do this in a couple steps. We're going to take 9.8 times 10 to the minus 9, and we're going to divide that by 4. Right, I'm going to divide both sides by 4. So then I'm going to move this up here. I get x cubed is now equal to 2.45 times 10 to the minus 9. Now, I know that some calculators don't have the cube root, so remember what you can do. Instead of doing a cube root, you can raise your answer to the 1/3. That's the way of doing cube roots with exponents, because a square root is just something raised to the 1/2. A cube root is something raised to the 1/3. Okay, so we can take, we know that x is going to be equal to 2.45 times 10 to the minus 9. The cube root of that can be done as 1/3. Okay, if you have a calculator where you have the cube root in your math menu, you can use that as well, or you could just raise it to the 1/3. Whatever works. So we get that raised to the 1/3. That gives us an x that's equal to 0.00135. And that's our molar solubility right there. That's our molar solubility. So we've solved for molar solubility, we did that. Now we want to solve for the solubility. So I'm going to bring my number up here to the top. That's 0.00135 moles per liter. Just move that over to here. And then we are going to convert that to grams per liter. So we need to look up the molar mass of lead fluoride, which is 245.2 grams per 1 mole. So that's going to cancel our moles on top and bottom, and we're going to take that 0.0135 and we're going to multiply it by 245.2. And that's going to give us a solubility of 3.31 grams per liter. Now, what does that value mean? That's how many grams of that substance will dissolve in exactly 1 liter of solution. So if I put in exactly 3.31 grams to exactly 1 liter of solution, all of that will dissolve. If I added any more, it would not dissolve because it would exceed that solubility. If you put less, then yes, it will all dissolve, but anything more than that would not dissolve. So now let's do some additional practice where instead of being given the KSPs, we're given the solubility and we want to solve for the KSPs. Now, as we saw in our last problems, the molar solubility was the x value that we were using from our ice table, or what we derived as x from our ice table. So if we're given the solubility, we're essentially given x, and then we can plug that into our ice table and solve for KSP. So just like we saw in ice tables when we first started learning them, if we know our k, we can find x, and if we know x, we can use that to find k. It's the same application. But again, with solubility, we have to do one step either before the problem or after. And in this case, we have to do one step before the problem because the x value that we use in our ice tables needs to be in units of molarity or moles per liter, which we have now defined as molar solubility. But here we're given solubility in grams per liter. So again, we're going to have to use our molar mass to convert from grams per liter to moles per liter. So that's going to be our first step in this problem. So let's do that. We want to take this 7.3 times 10 to the minus 2, and we want to convert that. Here, let's put some units on that. This is in grams per liter. We want to convert that to moles. So we want to have 1 mole on top and our molar mass on the bottom. The molar mass for strontium fluoride is 125.62 grams. So all we have to do is take 7.3 times 10 to the minus 2 and divide that by 125.62. And we get our molar solubility to be, 5.81 times 10 to the minus 4 molar, or moles per liter. This is now going to be our x value in our ice table. So let's set up that ice table. If we have strontium fluoride, SrF2, that's going to be in equilibrium with Sr2+, strontium 2+, and 2F-. So we set up our ice table. Again, we can ignore our first column because that's a solid. We know that this is a solid, so we can ignore that. Our initial concentrations of our two ions is 0, and it's going to increase by a factor of x and a factor of 2x. So we get here that it's going to be x and 2x. However, we know that x is going to be 5.8 times 10 to the minus 4. So our strontium concentration is 5.8 times 10 to the minus 4, and our fluoride concentration is going to be twice that, so 2 times 5.81 times 10 to the minus 4. And that's what, 1.16 times 10 to the minus 3. So now that we have these molar values, okay, our equilibrium values, we can now solve for KSP, because we know that KSP is going to be equal to the concentration at equilibrium of strontium 2+, and the concentration of F- at equilibrium that we are going to square. So remember, we're again counting for our balancing in two different places. We accounted for it here by multiplying that x value by 2, and we also account for it here by squaring that concentration. So what we can do is take KSP and plug in our values. So we have 5.8 times 10 to the minus 4 times 1.16 times 10 to the minus 3 quantity squared. And then we just plug everything in. So we'll square that 1.16, then we'll multiply that by 5.81 times 10 to the minus 4. And we get our KSP to be 7.84 times 10 to the minus 10. Another way that you could solve this problem, which again is the same math, same thing that you're going to be doing here, you're just doing it in different steps. You could take KSP and you know it's going to be x times 2x squared, which we know is going to be 4x cubed. You could then just plug in our x value of 5.8 times 10 to the minus 4 cubed. So if we plug that into our calculators, we get 4 times 5.81 times 10 to the minus 4 cubed. And we get the same exact number out. So you can do it either way, depending on how you see these types of problems. I personally like to plug in x and get those equilibrium values and then just plug that in for KSP. But if you're one that wants to think more in x, you can use this way as well. Either way works, they get the same number out. Okay, so we have another problem here. We want to do the same thing. We want to calculate the KSP, the solubility product, for silver phosphate with a solubility of 6.7 times 10 to the minus 3 grams per liter. So pause your video and try this problem on your own, following the same steps that we did for the first problem. The first step in this problem is taking that solubility and converting it from grams per liter to moles per liter. So we have 6.7 times 10 to the minus 3 grams per liter. And we are going to divide that by the molar mass, 418.58 grams per 1 mole. So we take 6.7 times 10 to the minus 3, and we divide that by 418.58. And we get out a molar solubility of 1.60 times 10 to the minus 5. And again, that value is going to be the x in our ICE table. So let's solve our ICE table here. Now I'm going to just quickly erase this. Okay, so we have silver phosphate, so our balanced equation is going to be Ag3PO4, which we know is a solid, in equilibrium with 3Ag plus PO4, 3 minus, giving us an ICE table like we had before. We ignore our first column because that's a solid. We start off with 0. This is going to increase by 3x, and this is going to increase by x. So our equilibrium concentration is 3x and x. And again, you can solve for this either way. You can either plug in your x value here that we just solved for, or you could go through the KSP and simplify, do some algebra with x, and then plug in the x value. Either way you do it, it's going to give you the same number as we just saw with our previous example. So x was 1.60 times 10 to the minus 5. So that means that 3x is going to be 3 times our answer. So 4.80 times 10 to the minus 5. Okay, so now we can plug those values in for KSP. So KSP is equal to the concentration of silver, so 4.80 times 10 to the minus 5. And then we're going to cube that, multiplied by our x value for PO4, so 1.6 times 10 to the minus 5. So let's plug that into our calculator. 4.80 times 10 to the minus 5 cubed times 1.6 times 10 to the minus 5. So we have KSP is equal to 1.77 times 10 to the minus 18. I believe we had 2 sig figs there, so 1.8 times 10 to the minus 18 for our KSP for that. So again, when we're given these types of problems, we have to convert our solubility to molar solubility so that we can use that value in our ICE table. Once we have our molar solubility, that can be plugged in for X and then used to solve for KSP. So between our past few examples, we saw how we can either be given KSP, use an ICE table to solve for the molar solubility, or how we can use the solubility or molar solubility to solve for KSP. Now we can predict if something is going to dissolve in solution or not, or how much will dissolve in solution. Because this is an equilibrium, we can utilize that K value, that KSP, to determine how much, or even if at all, that solid is going to dissolve. So, since precipitation reactions are in equilibrium, we can use values of Q and K to predict if the solution is either unsaturated, saturated, or supersaturated. So we're bringing back in our reaction quotient Q and relating it to our equilibrium product K, just like we did in our previous chapters, where we saw that the relationship between Q and K can tell us if we are favoring our products or our reactants, or which way the reaction is going to go. So we have 3 different types of solutions that we can have with precipitation reactions, or things that are soluble. The first is going to be unsaturated, and this is where ions can still go into solution. And if we're talking in equilibrium, that means we are moving towards the product. Okay, so if I can still create ions, that means I'm moving from my reactant to my product. So this means the reaction will proceed in the forward direction, which corresponds with what we already know about our relationship between Q and K. When Q is less than K, then the reaction is going to proceed in the forward direction, favoring the products. If we have a saturated solution, this is the maximum amount of ions that can be in solution at any given time. When we have a saturated solution, we consider our reaction to be at equilibrium. So when we say that it's the maximum amount of ions that can be in solution, we're at equilibrium, meaning that if I have ions going out of solution, that means a solid has to go into solution. So we're at that dynamic equilibrium where the rate of the forward reaction is equal to the rate of the reverse reaction. Okay, so we're at equilibrium. We cannot have any more ions be in solution. So here our Q value would be equal to K. We next have a supersaturated solution, and this is when we have too many ions or too much solid in solution, and we're actively forming a solid. Okay, we're actively taking out those ions and making our solid. So we're actually going in the reverse direction. Okay, there are too many ions in solution. We need to start forming our reactant. So we are moving toward the reactant side. Okay, so we're proceeding in the reverse direction, which we know that in equilibrium terms, if Q is greater than K, then the reaction is going to proceed from products to reactants, or in the reverse direction. So what we can do with this information is, if we're given concentrations of our ions or our solution, okay, Okay, we can compare that to the KSP value. Knowing how to calculate Q, we can say, yes, we can either put more ions into solution, or nope, we have enough ions in solution, we are going to be supersaturated and start forming solid again, or we're at equilibrium. So let's look at a practice problem that does just that. We want to predict whether calcium hydrogen phosphate will precipitate from a solution with a calcium ion concentration of 0.001 molar and a hydrogen phosphate concentration of 0.0001 molar, given that the KSP is 7 times 10 to the minus 7. Now we have to remember that this is asking if it will form a precipitate, so if we're going to form solid. So if we're forming solid, we would want to see a Q that is greater than K, because it would be favoring the reactant side, or moving in the reverse direction of our equilibrium. So are we going to be forming solid? Are we going to be forming a supersaturated solution where ions are actively coming out of solution and forming a solid? So we want to see if our Q is going to be greater than K. If it is, then we'll form solid. If it's not, then we will not form solid and we will not form a precipitate. So we know from our definition of Q is going to be equal to our products over our reactant concentrations raised to their end values. Okay, so the first thing that we have to do is write out our balanced chemical equation. So we know that CaHPO4 is going to be the solid that we desire, and it's going to be in equilibrium with Ca2+ and HPO4 2-. So that's a balanced chemical equation right there. Everything's in a 1-to-1 ratio. So Q is going to be equal to the concentration of the calcium ion times the concentration of the hydrogen phosphate ion. Remember, we don't consider the calcium hydrogen phosphate because it's a solid, so it won't participate in determining that equilibrium value or that reaction quotient. So all we have to do now is plug in our values of those concentrations. So we know it's going to be 0.00010 times 0.00010. So we'll take that, 0.00010 times 0.00010. And we get a Q value that is equal to 1 times 10 to the minus 8. We know our KSP is 7 times 10 to the minus 7. And comparing those two numbers, Q is going to be less than K. Remember, we're working with negatives here, so that negative exponent means that we're in decimal places. So KSP is going to be the larger number compared to Q. So Q is going to be less than K, meaning that no precipitate will form. Ions could still go into that solution because Q is less than K, so the reaction would still proceed in the forward direction instead of the reverse direction. Finally, I want to just bring up something that we discussed at the beginning of this chapter and relate it to what we're talking about here. So we talked about the common ion effect right at the beginning of the chapter, and we talked about it more so in the context of acid-base reactions. But because the common ion effect is something that applies to all equilibria because of Le Chatelier's principle, it also applies to precipitation reactions or solubility equilibria because we're still adding in ions. There are still ions that are creating that equilibrium. So, the solubility of an ionic compound is less when dissolved in a solution that contains a common ion. So if again, just like we saw earlier in this chapter, if we were to add in one of these ions, it's going to force the reaction in the reverse and create more solid. That would then decrease the solubility, the amount of solid that could go into solution. It would decrease that solubility because of the common ion effect and Le Chatelier's principle. You're adding a stress into the product side, which then forces the reaction to the reactant side. So here, if we add silver or iodide ions, the reaction would move in the reverse direction, causing more of the solid precipitate to form, thus decreasing the solubility.